All right, so in this video, we're going to be looking at calculating a solution to a system of three variables using Cramer's rule. Now, Cramer's rule involves using various determinants in order to calculate the solution. I have a video that I'm going to post that calculates determinants for 3x3 systems. We are not going to do the by hand manual calculation of the determinants in this video. Instead, I'm going to use technology to calculate the determinants so that we can focus on the procedure for solving the problem with Cramer's rule. Now, the general idea for Cramer's rule is that the coefficient matrix is going to be our sort of base determinant. We'll call A, and we'll need the base determinant for that. But then each of the variables is going to depend on the determinant for a matrix where the corresponding column of coefficients from the original matrix is replaced by the constant vector from the system. And so we're going to call those A sub I, just so that we have a consistent notation. Now that means we're going to treat the subscripts. X will be the first subscript, correspondingly Y will correspond to the second subscript, and Z will correspond to the third subscript, as if we were using X sub 1, X sub 2, X sub 3. Now the A matrix, therefore, is going to look like this. Again, it'll be 1, 1, 1, 1, -6, 3, and 5, 2, 2. Now, the A1 matrix is going to look exactly the same way, except we're going to replace this first column with these constants. So we're going to replace this with 2. We're going to replace this with 18 and this one with 13. The A sub 2 matrix is going to make the same swap, but in the second column. So if we go back to the A matrix, it's this now second column that's going to become 2, 18, and 13. And then our A3 matrix is again going to replace the third column with our constants, 2 and 18 and 13. And then each of our solutions is going to depend on the determinant of, in this, X will be depending on A1 divided by the determinant of A. And so this absolute value notation is a linear algebra notation for the determinants. The Y coordinate, our second coordinate, is going to depend on the determinant of our A2 matrix divided by the determinant of our A matrix. And then the third coordinate, Z, will depend on the third matrix divided by the determinant of the original matrix. Now let's go ahead and calculate these determinants. Now, again, I'm going to use technology to do this calculation. So I've entered my original A coefficient matrix into my calculator. That's this one. And I'm going to use the determinant function in order to calculate that determinant. And I'm getting 27 for that one. So this determinant of the A matrix is 27. And so that's going to go in the denominator of all of our solutions. And now we're going to need to calculate the determinants for our A1, A2, and A3 matrices. Now, again, I'm going to use technology for this. I'm going to go into my calculator and I'm going to modify the first column into the 2, 18, and 13. And then I am going to calculate the determinant again. And in this case, I'm getting 81. And 81 divided by 27 is 3. And we solved this system in another video, and that is the correct value for X. For my second matrix, I'm going to, again, go into my calculator. I have to put the first column back and then replace the second column. And when I have completed that, I'm going to calculate the determinant, and I get minus 54. And if I divide minus 54 by 27, I get minus 2, which is, again, consistent with the answer we had for the system in a previous video. And then finally, we can do this to our third example. And again, I have to put the second column back and then replace the third column with the constants. And then when I calculate that determinant, I get 27. And 27 over 27 is 1. And again, this is 3, negative 2, 1 is the same solution that we got to the system when we solved it by row reducing in a previous video. Now, Cramer's rule is computationally quite intensive because you are doing all of these determinants. Determinants are not, by any stretch of the imagination, easy to solve by hand. The one advantage that I can see for Cramer's rule for larger systems is that you can, in fact, solve for just a single coefficient, single variable. So if you really only care about the value of one variable and not all 3 variables, you may be able to save yourself a little bit of work by only having to solve for one of them instead of all 3 of them. However, solving by row reducing is actually computationally more efficient, and then you get all of the solutions. So most people don't solve systems by Cramer's rule, and anything really bigger than 2 variables is going to become increasingly difficult because the determinants become increasingly difficult. But it is interesting to see that there is this other solution process that we can use that is also going to get us the same answers, but with using completely different aspects of linear algebra.